Let us look at some more examples. So let us look at example number 4. Let us take the set X to be equal to R2 and C is the collection of all rectangles in R2. So let us just look at the picture and try to understand. So here is R2. So let us take a, can I say empty set is a rectangle? Of course, empty set can be written as A comma A cross A comma A if you like. It doesn't matter. Or you can also write as A comma A cross C comma D. In both cases it is the empty set or any other such representation. So empty set is an element of the collection of all rectangles in the plane. What about the whole space X, that is R2? Of course, that is R cross R, and R is a rectangle. Oh, sorry, R is a interval. So R is an interval which we write normally as minus infinity to plus infinity. So empty set is an element of it. The whole space is an element of it. Let us take two rectangles and see whether the intersection of these two rectangles is also. So let us take one rectangle here and another rectangle. The possibilities are they don't intersect. In case they don't intersect, then there is nothing to prove, because the intersection is an empty set which is already a rectangle. So let us take a rectangle which intersects with the earlier rectangle. So we are taking two rectangles R1, say R1 and R2, and R1 intersection R2, we want to check whether that is a rectangle or not a rectangle. But let us, from the picture it is quite clear that R1 intersection R2 is this rectangle. So is a rectangle. One can write down a formal proof by writing this to be equal to A, B, C and D and so on, but that is not necessary once we understand from the picture that intersection of two rectangles is again a rectangle. Of course, let us verify the third property, namely, can I represent the complement of a rectangle as a finite disjoint union of rectangles? So let us take a rectangle. So let us take a rectangle in the plane, this one. So this is a rectangle R, and I want to write R complement. I want to see what does it look like. Can I represent this as a finite disjoint union of rectangles again? Well, let us obviously in the picture I can try to do is the following. I can draw lines passing through the sides, and I can draw another line passing through this. Then it's quite clear this complement of R. So this was the set rectangle R, and its complement is nothing but a rectangle R1, a rectangle R2, a rectangle R3, a rectangle R4, rectangle R5, R6, R7 and R8. And of course, these rectangles R1, R2, R3, R4, R5, R6, R7 and R8. So this is R5, this is, and this part is, there are many ways of, so I am looking at this whole infinite, I can look at this whole infinite, this side and this corner as a rectangle and this part as a rectangle. So I can write it as union of Ri, I equal to 1 to 8, where Ri intersection Rj is empty, right? So it's a matter of writing down the details, that depending on in R whether which part of the boundary is included or excluded. Accordingly, I can make this rectangles Ri's to be disjoint. So this is true that the complement of a rectangle in the plane is also a rectangle. So that means what? That says that the collection or C of all rectangles in R2 is also a semi-algebra, of subsets of X. So we are given a lot of examples of objects which are semi-algebras of subsets of X. Now let us go to a next stage of understanding, extending this concept of semi-algebra to what is called an algebra of subsets of a set X. So let X be a non-empty set, and a collection F of subsets of X with the following properties. 1. Like semi-algebra, the empty set belongs to it, the whole space belongs to it, and of course there is another property which, so let us write, let us write this. So X is a non-empty set, F is a collection of subsets of X with the following properties. 1. If empty set and the whole space belong to F, like that in the semi-algebra. And secondly, we are going to look at the intersection property. If A and B belong to F, they are elements of F, then that implies their intersection also belongs to F. And of course, the third property, namely, in the case of semi-algebra, if I take an element F in F, then its complement need not be in F, but we were able to represent it as a finite disjoint union of elements of that class. But in an algebra, in the new concept, we are demanding this implies a complement also belongs to F. In these cases, we say F is an algebra of subsets of X. So this is called an algebra of subsets of X. So let us, so how does the algebra differ from a semi-algebra? This property, that is all true for algebra as well as semi-algebra. This property true for algebra as well as semi-algebra. This property may not be true for a semi-algebra. Namely, in that case, you recall we said a complement is a finite disjoint union of elements of F, and here we are saying a complement itself is an element of F. So let us look at some examples of this again to understand. So first observation, of course, every algebra is also a semi-algebra, right? Because of the third property that we looked at, namely in a semi-algebra, one would like to have a complement to be a disjoint union of elements of F. In algebra, it is itself in F, so it is much stronger. So every algebra is also a semi-algebra. Let us note, when X was equal to R and the C is equal to class of all intervals, we showed that C is a semi-algebra. That question, is C an algebra? Obviously, the answer is no. For example, I can take an interval, any non-degenerate or any interval, say A to B. Let us take this interval A to B, that is my I. So I belongs to C, but I complement is not an interval, because I complement is nothing but minus infinity to A union B to plus infinity. So when I belongs to C, I is an interval, its complement need not be an interval in general. So that implies that this collection C is not an algebra. So let me emphasize again, property here one says every algebra is also a semi-algebra, and this says every semi-algebra need not be an algebra, means there are examples of collection of subsets of sets. For example, in the real line, the collection C of all intervals is a semi-algebra, but it is not an algebra. So a collection of subsets is an algebra is a much stronger property, is a concept than that of a semi-algebra. Let us look at some more examples. Let us look at the example, same example of x is real line, C is all intervals. We know that this collection is not an algebra, it is a semi-algebra. Let us write F to be the collection of all subsets of the real line, such that, look at this collection of all intervals was not an algebra, because the complement of an interval need not be an interval, but it looked like is union of two disjoint intervals. So let us write where E such that E complement is equal to a union of intervals I equal to 1 to 2, where I intersection Ij is equal to empty. So what we are saying, look at all those subsets of real line which can be represented as disjoint union of two intervals. So claim F is an algebra. We claim that this is an algebra of subsets of R. So let us first make some observations, namely C is a subset of F, right? Because if I take an interval, okay, if I take an interval, then it has this property, namely it is a disjoint, its complement is a disjoint union of two intervals, right? So C is part of subsets of X. So this as a consequence implies empty set and the whole space belong to F, right? Okay. Let us look at the second property. Let us look at two elements. So let us call E1 and E2 belong to R. Sorry, E1 and E2 are elements of C. We want to check whether E1 intersection E2 belong to C or not. So what is E1? Because E1 belongs to C implies E1 complement can be written as a disjoint union. So this square bracket normally indicates that I am writing something as a disjoint union. So I11 I equal to 1 to 2, or let us just simply write it as is a union of two intervals. So I11 union I12, where both of these are disjoint. Similarly, E2 complement can be written as a disjoint union, let us call it J11 union J12, where J1 and J2 are disjoint. So, but now we want to look at E1 intersection E2. We want to look at E1 intersection E2. Okay, and we want to check whether this belongs to C or not. That means what? I should look at E1 intersection E2 complement and try to represent that as a union of two intervals. So, let us look at this is equal to E1 complement. Here is intersection. So, by De Morgan laws that becomes E2 complement. Okay. Now, this is same as E1 complement is nothing but I11 union I12 union E2 complement, that is J11 union J22. Now, from here I1 and these two are disjoint, but all of these four may not be disjoint, right. So, this set of ideas seems not leading us to a claim that F is an algebra of subsets of X. So, let us modify our arguments. So, instead of checking this second one whether the intersection belongs to it, right, let us look at the property, the third property that we want, whether that is true or not. So, what was the third property? That property said if a set E belongs to C, right, we want to check an algebra. So, let us look at E belongs to F. Does that imply E complement belongs to F? Right. So, let us take a set E belonging to F. Okay. Now, what is E complement? E complement looks like a finite disjoint union of elements because E belongs to it, so it is a disjoint union of two elements. So, E complement is equal to E complement is I union J. So, it seems to suggest that if I can show that the collection of finite disjoint unions, this F is closed under union, then I may be through. So, we modify all our arguments again and see how do we proceed. This is how one does not get all the time a polished proof in mathematics. One has to modify the arguments. So, I modify my arguments to prove that F is an algebra as follows. So, the first step, so let us keep in mind what are we trying to do. So, here is the collection F of subsets of X, subsets of the real line, which are union of two of them. But that seems to complicate the issue. So, instead of this, let us modify this definition of F itself and let us look at the modified version of this example. X is real line. Let us look at F, the collection of all those subsets E of R such that instead of seeing E complement is a union of two disjoint intervals, let me just write E complement is equal to a finite disjoint union of intervals Ij, j equal to 1 to n, where Ij's are intervals and they are pairwise disjoint. So, that is already indicated by writing this square bracket. So, now let us observe, keeping in mind our previous arguments, that C, the collection of all intervals is a part of F. So, that implies that empty set and the whole space are members of F. Second, now if E and F belong to this collection, then what is E? E is a disjoint union of intervals. So let us write E1 union E2. I can write this as E1 is a disjoint union. So let us write E1 as union of I j, j equal to 1 to n, union of disjoint union of some I j k, k equal to 1 to m. Now these collection of sets intervals are disjoint, this collection of intervals are disjoint, but all of them may not be disjoint, but that does not matter much. I can write this as union over j equal to 1 to n, union over k equal to 1 to m of ij intersection jk. So what I am doing is I am intersecting. So the basic property is if two intervals are not disjoint, then I can write them as a union of disjoint pieces. So this collection of intervals is a union of intervals which may be overlapping, but I can intersect one with another and write this as a disjoint union. Now these pairs of intervals will be disjoint. So that implies this. So this will imply that if E and F belong to F, then that implies E union F also belongs to F. So this collection of finite disjoint union of intervals is closed under unions. And let us write finally that if E belongs to F, then that implies by definition E complement is a disjoint union of intervals, and each ij is an interval, so it belongs to F, and just now we proved it is closed under unions, so this implies this also belongs to F. So the collection of sets of the real line which are finite disjoint union of intervals have the property C is a subset of it. If E and F belong to it, then it is closed under unions and also closed under complements. Now it's a simple matter for us to check that these two properties, whenever a collection of sets is closed under unions, E F belonging to F, we showed implies E union F belongs to it, and also E belonging to F implies E complement belongs to F. But these two properties imply that E intersection F also belongs, because I can write this as because I can write E as E complement okay, union because what is the complement, if you like, this intersection of E F complement, and that I can write as E complement union F complement complement. Simply just saying that because this is De Morgan's laws, this will give you E complement intersection. Now E belongs to F, so this belongs to F, this belongs to F, this union belongs to F, and complement belongs to F, so this belongs to F. So basically in an algebra, if F is an algebra, then saying that it is closed under unions and complements is equivalent to saying it is closed under intersections and complements. So let us just summarize what we have done today. We started by looking at our course measure and integration, and I said the underlying set of real numbers need to be extended to a larger class, namely the set of extended real numbers, and there we defined the notion of order, addition and multiplication, and analyzed how the sequences, series, supremums of sets behave there. Then we started at looking at collection of subsets of a set X with some properties. We started at, the first thing was we looked at what is called a semi-algebra of subsets of X. Namely, it is a collection of objects, subsets of the set X with the property empty set and the whole space belong to it. It is closed under intersection, and the complement of any set in this collection is representable as finite disjoint union of elements of that collection again. And a typical example was that of all intervals in the real line. Then we looked at a slightly stronger concept, namely the algebra, an algebra of subsets of a set X, which we defined as the collection with the properties empty set and the whole space belong to it. It is closed under intersections and also closed under complements. And then we made a remark, every algebra is a semi-algebra. The collection of intervals in the real line form a semi-algebra, but they don't form an algebra. And we showed how to construct an algebra out of these intervals. Namely, we looked at the collection of all finite disjoint unions of these intervals, and that collection we proved it is an algebra of subsets of it. So we'll continue analyzing such collections of objects in our next lecture. Thank you.